Everyone, welcome to homework 4.6. Today we are going to go ahead and get started by looking at scenarios in which gravity or some other force is bringing something back down, right? And so we looked at some quadratic functions that represent those situations and analyze them. And so this will further do that. All right, so we're going to start by looking at the height of a diver, and it's given by this equation here, where t is measured in seconds and h of t is measured in meters. So we're talking about seconds and meters. Select all statements that are true about the situation. So the diver begins 5 meters above water. Yes, we might be tempted by that, but this is not the starting point. The starting point is here. So it's not A, it's going to be B. The diver begins 3 meters above the water. That constant there that we're adding there is going to be where we start. The function has 1, 0, and that makes sense in the situation. So assuming the diver is above the water and then going into the water, it wouldn't make sense that they have two zeros because we know that they're starting at 3 meters above water. So any time before that would be negative time, and so we wouldn't really consider that. So this, sorry, rather, is that it has 1, 0 and that two zeros don't make sense in this situation. Letter E, the graph that represents H, starts at the origin and curves upward. So starting at the origin would mean that if we were to look at the graph, it starts here, but we know that the starting point is actually starting at 3, so it's not starting at the origin. And it says the diver begins at the same height as the water level. So no, because again, we have this plus 3 there. So B and C are our best answer options. Number 2, the height of a baseball in feet is modeled by the function h given by this equation. So we see our gravity is taking some into account here. And the graph of this function is shown down here. When does the baseball reach its maximum height? So that would be sometime between 1 and 2 seconds, closer to 2. So we would say probably like 1.9 seconds. It does say about when, so we'll go ahead and estimate here. How high is that then? So it looks like it's just under 60, say maybe 59 feet. And it says about when does the ball hit the ground? And so that would be here right before 4 seconds, maybe 3.75 seconds. It's not quite 3.9, it's somewhere in between there, maybe 3.8. Um, now, as a reminder, because we were practicing using our technology, we could plug this function in. Um, uh, plus 60t, that's our velocity, plus 3 is starting height. And we could take a look at what this graph looks like. And we can also find more specifically by doing second calc. Let's find our maximum. So that's 4. So left boundary, enter, and then I'm going to go to the other side of the graph. When I can see it on the other side, I'll know I'm on the right. Oh, too far. Right boundary, enter, guess. So our maximum here, it looks like, is 1.875. So we guessed 1.9, so 1.875 seconds. And that tallest point there is 59.25. So we were pretty close there. And then we can also look at exactly the zero. So let's do second calculate and calculate a zero. And we're going to go, oops, too far. Let's go there. That's to the left of this point there. Looks like above, but it's to the left of. And then we're going to go to the right and say guess, and our zero is 3.799. And so, again, pretty close there by our estimate of the graph. A little maybe closer to 3.8 there. All right. So two rocks are launched straight up in the air. The height of rock A is given by the function f, where f of t equals, here's our equation here. Again, gravity is taken into account. And then there's rock B, which is this equation here. In both functions, t is measured in seconds and height is measured in feet. Use graphing technology to graph both equations. Determine which rock hits the ground first and explain how you know. Describe what you see in the graph. All right, so let's go back to our y equals and graph these. Um, Helpful hint if you're at home and you did not bring your calculator, you can also graph these in Desmos and analyze the graph in Desmos. To be honest, it's a lot easier to look at it in Desmos. However, that just won't be the technology you have for the park test or CAPE test, whatever we want to call it now. But it'll still let you see the graph pretty nicely. And I messed up there. That should be 16. Okay. So notice our starting points are different, which we can see. Our first equation that I input is f of t, which is the blue line. Our second equation is g of t, which is the red line. I'm going to go ahead and change my window here because we don't really need to look at negative values. I'm going to put -1 just so we can see a little bit beyond there. And then the x max, I'm going to do 20 seconds. I don't think it'll take longer than that. Same thing, I'll do -1 to the y value just so we can see a little bit more of the axis there. And then I know that this rock is going to be, starting at 4 feet and going by increments of 30 to 20 feet, depending on which equation I'm looking at. So I'm going to go ahead and for now put this at 100, just so that that's maybe the tallest point. Let's see what we get. So when I hit graph, oh, 100 was way too big. So let's go back out and window, and I'm going to change this to 25. Let's see what we get there. Okay, that's a little bit better. I could probably reduce that even more. So this looks like it's actually hitting the ground pretty quickly, and 10 is probably also too big, or 20 is too big. Let's do 10, and let's do 20 here and see what happens. So that's a lot better. We can see that a lot better. So remember, my blue graph is f of t, and my red graph is g of t. So f of t, it looks like, goes up to a higher point and then lands later. And then g of t doesn't go up quite as high and therefore lands a little bit earlier. So you can go ahead and draw out a little graph here for yourself. It doesn't have to be exact, but you want to show, right, that our blue graph, or f of t, is starting lower, going up higher, and taking longer to land. And our red graph, or g of t, is starting higher, right? It starts at 5, but because the acceleration is less, it doesn't go up as high and it comes back down faster. That's not the most perfect graph, but it's not terrible either. Here, we would want to say that f of t, which is our blue line, will actually, let me rephrase that. Let's say g of t will hit the ground first because its x-intercept, or its 0, is before that of f of x. And again, we know this because this right here, that greater, or that less velocity, means that it's not going to go up as high, whereas this one has a greater velocity, so that speed is going to push it up to go a little bit further before gravity brings it back down. All right, number 4, each expression represents an object's distance from the ground in meters as a function of time, t in seconds. So 2 equations here again. Notice our starting points are different, and again, we have different velocities, but we still have that object's distance from the ground in meters as a function of time, working out pretty nicely. So which object was launched with the greatest vertical speed? So here we have the greatest vertical speed at 50t, so this would be object B. Which object was launched from the greatest height? So this one is our greatest height there, is object A. Tyler is building a pen for his rabbit on the side of the garage. He needs to fence in 3 sides and wants to use 24 feet of fencing. All right, so we have a width times the length, right? And he's going to be using 24 feet of fencing. The table shows some possible lengths and widths complete each area. So this is the table already gives us this, so you don't need to write anything here. We're going to fill the table in. So the area here would be 8 times 8, which is 64. All right, again, a possible area here would be 70. Here we can do 72. This would be 14 times 5 is 70. 16 times 4 gives us 64. All right. It says, which length and width combination should Tyler choose to give his rabbit the most room? So based on this information, we would want him to have um, the one that is 12 by 6. All right, here is a pattern of dots. Um, Complete the table. How many dots will there be in step 10? All right, so remember for these, this is quadratic, so we want to look for what is the pattern here, right? So in step 0, I have 3 dots. In step 1, I have 1, 2, 3, 4 dots. So if we think about the square here of 1, would just be that one plus those 3, okay? Here is the square, and then I'm adding 3. So notice that in each case it appears that I am adding 3. Let's see if it works here. So this is 3 times 3 plus 3. So it would be the step number squared plus 3. We could go ahead and plot this out. For step 10, we would have a 10 by 10, and then we would have an additional 1, 2, 3 dots added there. So that would be 103. And step n then would be n squared plus 3. All right, we can again fill out our table here, which is 3, 4. This is 7. Then we have 9 plus 3 is 12. All right. Number 7 says the function f, so this is defined by 2 to the power of x. So this gives us an exponential function, and this one is a quadratic function. Find the values of f and g when x is 4, 5, and 6. So you can use your calculator to do this the easiest way, right? 2 to the power of x, and then x squared plus 16. And the second table will give us our points. So for 4, 5, and 6, we have 4, comma 16, 5, comma 32, and 6, comma 64 for the first f of x. That's f. And then g would be 4, comma 32, 5, comma 41, and 6, comma 52. It says, are the values of f of x always greater than g of x for all of x? Explain how you know. So, no. So prior to, looks like prior to 5, so between 0 and 5, g of x is greater. And then after 5, f of x is greater. So again, always our exponential functions will outgrow our linear and our quadratic functions. All right, Han accidentally drops his water bottle from the balcony of his apartment. The equation d equals 32 minus 5t squared gives the distance of the ground d in meters after t seconds. Complete the table and plot the data on the coordinate plane. All right, so if we're using this equation, after 0 seconds, at 0 seconds, it's 32 feet, right? That's how tall the balcony is, presumably. And again, this is in meters, so that's why it's 5 and not 16 here. And then 0.5, so we want to put into our equation 32 minus 5 times 0.5 squared gives us 30.75. And then 32 minus 5 would give me 27. And then 1.5, we're going to do 32 minus 5 times 1.5 squared will give us 20.75. And then 2 squared is 4. 4 times 5 is 20. 32 minus 20 is 12. All right, so then we can graph these points. So we have 0, 32. 0.5 is 30.75. 1 is 27. 1.5 is 20.75. And 2 is 12. All right, so we have something that looks kind of like that, okay? Is the water bottle falling at a constant speed? No, because this is quadratic, you can say. And it is not losing the same amount of distance each second. Right, so each second that we look at, right, this distance at first is a small distance that's falling. Then by the time it's getting close to the ground, that distance that's falling is a lot greater. All right, number 9, the graph shows how much insulin in micrograms is in a patient's body after receiving an injection. Assume the amount of insulin continues to decay exponentially. So we know in this case we're looking at an exponential function. Write an equation giving the number of mcg of insulin, M, in the patient's body each hours after receiving the injection. So we are going to say that M equals, starting amount is 200, times whatever our factor is going to be, and it's what percent is left each time, to the power of H. So here we go from 200 to, it looks like 80. So we can do 80, oops, 80 divided by 200 should give us 40% or 0.4. That's how much is left each time. And we can check to see if that makes sense. If we do 80 times 0.4, we get 32, and that looks to be about where this is right here. It says after 3 hours, will the patient still have at least 10 mcgs of insulin in their body? Explain how you know. So let's try it. 200 times 0.4 to the power of 3 gives us 12.8. Yes, she will have, or he, I don't know if it says, they will have 12.8 mcgs left because 200 times 0.4 to the power of 3 gives us 12.8. Okay. We can also consider that, right, this is about 32 here, and so 40% of 32 gives us 12.8 as well. So you can calculate it that way. All right, your code word for today will be, oh, you know what? Let's use something related to our words of the week. Your code word today will be equidistant. Equidistant is your code word. Happy homeworking and see you tomorrow.